Okay, so now we're going to move on to lines and the vector equation of a line. So we've gotten the vector equation of a plane. We've gone from ABC to so now what we want to do is we want to go from to something. So the first thing we're going to do is we are going to draw a line, call it L, and this line is in the direction of some vector u, where u is non-zero, or else it doesn't have a direction. And then we are going to say a point P on L. Okay, so L passes through this point P, and we're going to put on another point R, and this point R will vary, and we will say that R is on the line L if and only if the vector PR, the bound vector PR is parallel to U. So let me show you why this makes sense. If R was not on the line, then if R is anywhere apart from on the line, remember U is in the direction of L, then PR cannot be parallel to U. I think that was simple enough. So only when R is on the line, then this vector here, this bound vector, is parallel to U. And one way of writing something, saying something's parallel, is to say that the free vector represented by PR is equal to some lambda U. And remember, these are position vectors. So if I was to go PR, then this vector PR is R minus P. So it's right there. R minus P is equal to lambda U. Hence R is equal to P plus lambda U, where R is some point, it could be on the line, P is some point that passes through the line L, and U is in the direction of L. And this is the vector equation of a line. I guess you can try look at similarities between y equals mx plus c, c being a point on the line because it intersects, m being the direction of the line, yes, yeah. If m changes, then the direction of the line changes, but this doesn't matter. Now, this is the vector equation, and there are two other forms of this line. So R is equal to, if we then set R is equal to x, y, z, because remember this is a position vector, and then P is equal to P1, P2, P3, and U is equal to U1, U2, U3, then we have x, y, z is equal to P1, P2, P3 plus lambda U1, U2, U3. Now, if you remember from previous videos, xyz is the same xi plus yj plus zk. And I'm going to do it for the top line alone, just show you what happens. So we have xi is equal to p1i plus lambda u1i. And the i's can, should I just do it for the whole thing? No. The i's cancel out. I think this is, so x is equal to p1 plus lambda u1. Now we can do that for the rest of them, so y is equal to p2 plus lambda u2, z is equal to p3 plus lambda u3. And this is now what we call the parametric equation of the line L. So this was the vector equation, this was the parametric equation. Now there's one more form, the Cartesian equation. X is equal to P1. I'll just write out again. And to do this, all we do is we solve for lambda. So this implies that x minus p1 over u1 is equal to lambda, and so on, y minus p2 over u2 is equal to lambda, and z minus p3 over u3 is equal to lambda. So then x minus p1 over u1 is equal to y minus p2 over u2, which is also equal to z minus p3 over u3. And this is the Cartesian equation of the line L. And so let's do a quick, what one should we, okay. So if I was to give you an equation such that 1, 2, 3 is equal to 4, 5, 6 plus lambda 1, 0, 1. This line L, sorry, I've written in the XYZ part. So R is equal to 1, 2, 3 plus lambda 2, 3, 4. So this line L passes through the point 1, 2, 3, and it's in the direction of the vector 2, 3, 4. Now, if I wanted to find out if a point was on this line, then I'll just put it into this equation. So if I then ask if 3, 6, 9 was in the equation, then I'd say that's equal to 1, 2, 3 plus lambda 2, 3, 4. Taking minus in 1, 2, 3, we have 3 minus 1, which is 2, 6 minus 2, which is 4, 9 minus 3, which is 3, is equal to lambda 2, 3, 4. And as you can see, 2 is equal to lambda 2, that means lambda must equal 1. But when lambda equals to 1, then 4 equals 3, which is not right. So this point is not on this line. Should we find a point that is on the line? So we'll check if the point, let's see, okay, so we'll check if this point is on the line. 1, 2, 3 is equal to lambda 2, 3, 4. So if we do the minus again, 5 minus 1 is 4, 8 minus 2 is 6, 8 is equal to lambda 2, 3, 4. And lambda has to be 2. If lambda is 2, 2 3 is 6. So this point is on the line, and this equation is satisfied when lambda equals 2. And we can use the other equations as well. We don't always need to use the vector equation. I'll leave that as like an exercise. But that's how you find out if a point is on the line, given the equation. And remember, the first bit is the line passes through this point, and the second part is the direction of the line. Or actually, we'll do one more exercise because sometimes they don't give us the direction of the line. Sometimes the direction of the line is not given, so they might say a point 2, 3, 4, and another point Q, which is 3, 4, and 5. So what we have is 2 points, and they want the line that passes through both these points. So if I just draw it, this is P, this is Q. Well, you know the direction of this line is going to be PQ, and PQ is just Q minus P. So where Q represents the position vector of Q and P represents the position vector of P. So that's 3 minus 2, which is 1, 4 minus 3, which is 1, 5, oh, yes, 1, 1, 1. It's in the direction of the vector 1, 1, 1. And if you remember the equation of the line, R is equal to some point of the line, so I can use either 3, 4, 5 or 2, 3, 4, plus lambda multiplied by the direction, which is 1, 1, 1. And then we can convert it into Cartesian equations if we want by just changing R to be x, y, z, and so on.